everyone, welcome to our channel Knowledge of Friends. Subscribe to our channel and click the bell icon for the latest update. आज हम लोग करेंगे प्रिंसिपल ऑफ प्रोग्रामिंग लैंग्वेजेस का क्लास, जो कि क्लास नंबर 4 है. ऑलरेडी हमने क्लास 3 कर लिया है, जिसमें हमने यूनिट 1 ऑलरेडी कंप्लीट कर लिया है एंड यूनिट 2 स्टार्ट भी कर दिया है. That is, your unit 2 is your language properties, and in this we had completed few questions related to your exams. And first of all, it's a huge request from my side to all the viewers, please go through the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Now today we'll start with the language properties, and the question will start with how the data structure is implemented to represent the storage. And before that, first of all, please go through with the subscribe button and please like, share and subscribe our channel. Let's go ahead and begin with the classes. That is how data structure is implemented to represent the storage. In this, if I'm talking about here, this is the implementation consideration. In this, the data structure is implemented to represent the storage, where the implementation considerations for the data structures type that include the same issues as for elementary types, and in addition, the two new issues that develop that strongly affect the choice of the storage representations, that is efficient selections of component from a data structure and efficient overall storage management for a language implementation as well. Where we'll go ahead with a diagram here, that it is a descriptor, then we have a component, then again we have a component, then we have component, and again we have a component. This is how the descriptor goes to the component, then component goes to the component, and as well as component goes to the component, and again components goes to the component. This is known as linked representation. Within the same case, if I'm talking about, so here the another one is your sequential representations, where we have a component set once and they are linked that is sequentially, and that comes under in it, and that is known as in the form of component. This is component, 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 and again we have a component as well. This is known as sequential representation. So here in this, first of all, we have a descriptor, then we have component, again we have component, component, and component. Here we have component, component, then component, component, and again we have component as well. So this is sequential representation. This is a linked representation, where the storage representation for a data structures that include the storage for the component of the structure and the optional descriptor that stores some or all of the attribute of the structure as well, and the two basic representation, where the sequential representation are used for a fixed size structures and sometimes for the homogeneous variable size structures such as the character strings or stack. Linked representations are commonly used for the variable size structures such as list here. Okay, so in the terms of it, and now we'll go ahead with the detail. The another question what they can ask you about it, that what are the basic problem that is associated with storage management. basic problems associated with storage management. So what were the storage basic problems that is associated with storage management here, where the two central problems in the storage management arises because of the interplay between the lifetime of the data objects and the access path to it that exists as well. In the same case, while going through it, first problem that is associated, the basic problem that is associated with the storage management, that the first problem we have is your garbage. In the garbage, when all access paths to a data object that are destroyed, but the data object continues to exist, the data object is set to the garbage here, and the data objects that can no longer be accessed from the other part of the program, so it is of no further use. And however, the binding of the data object to storage location has not been broken, so the storage is not able to for reuse, and the garbage is a less serious but still the troublesome a problem as well. The second we have is your dangling references. In the dangling references, a dangling references is an access path that continues to exist after the lifetime of the associated data object, and an access path ordinarily reads that leads to the location of the data object, that is the beginning of the block of storage for the object, and at the end of the lifetime of the object, this block of the storage is recovered for the relocation at some data point to the another data object. And however, the recovery of the storage block does not necessarily destroy the existing access path to the block, and thus they may continue to exist as dangling references. Dangling references are particularly a serious problem for the storage management because they may compromise the integrity of the entire runtime structure during the program execution. For example, an assignment to a non-existent data object via dangling references that can modify the storage already allocated to the another data object of an entirely different type, thus violating the security of the type checking structures. Or it can be modify housekeeping data such as linked to be a free space list and that has been stored there temporarily by the storage management system, and thus destroying the integrity of the storage management system as well. Talking about these two are the basic problem that is associated with the storage management here. Now we'll go ahead with the further one, and that is the another question what they can ask you is all about, that is the discuss implementations of vectors with reference to a virtual origin, that we will discuss, and the full descriptor representations of a vector as well. We'll draw a diagram for that as well. So here implementation of vector with reference to virtual origin. So here let us address the element with the subscript 0 and of a given vector. So the assessing formula should be like the L value. For that, a of 0 is alpha minus lb, abstract that e and plus 0 alpha minus. So that has been represented here. I will just write it down for the L value, which is a of 0 is equals to alpha minus lb e plus 0. So that will be representing in the form of alpha minus lb stick e equals to k. This is will be equals to k here, where k represent the address at the element 0 of the vector that would occupy if it is existed. And in this same case, because the zeroth element may not be a part of the array, because the array may have a lower bound greater than 0, and this address is called the virtual origin. That is your, we can say that stands for VO. And this then that gives an algorithm for a building vector and generating the accessing formula as well. On creation of the vector storage, that allocate the storage for the n components of the vector of the size e, and that the descriptor size d as well, that allocate d plus n abstract e, that is the memory location, and then call address where the first vector element is stored. Then we'll compute the virtual origin. That is, your virtual origin has been represented in the form of alpha minus lb abstract a. So on accessing a vector component, that the L value of the component a of 1 is computed, and that is the L value of a of I, and that is that has been represented in the form of VO plus 1 abstract a, and that the prior formula that assumes that the value of the I is known to be a valid subscript for the a, and to check that subscript range error, that the test LB that should be less than equals to I, and that is also less than equals to that the virtual the value has been proceed and must proceed using the accessing formula for the value of the both LB and the VB here, that must be present in the runtime descriptor, and in general that the exact variations of the accessing calculation and the range checking, and this is most efficient, that depends on the particular hardware configuration and the hardware operations available. It is this range test which ensures that even if the subscript I is not within the range, which is LB is less than equals to I, and that is less than equals to VB as well, and that the storage that can never be accessed as a L value which does not represent a valid subscript. And note that the prior accessing formula that uses the virtual origin to determine as well. We will go ahead with a diagram with this which is representing the full descriptor representations of the vector A, and we will discuss about it in a detail as well. So this is sort of so this is your vector. Then we have LB, then we have UB, we have integer, then we have E, then of course we have stop, this is then we have colon, this is here, and then we have colon, and then we have stops as well. Here where this is your data type, and this is your that is your lower script bond, this is your upper script bond, this is your data type of component, this is your the another one is your size of component. A is your size of component. Then you have your A of LB, this is your lower bond, and A of LB plus 1, and then you have your A of upper bond, where from a vector till this E, this is your descriptor, and this is for the vector, it is your based address of a vector, and from this after E here, still this is the end of it. This is your storage representation of component, and this is all comes under in it, that is your full descriptor representation of vector A. In this, that where a given array element is located, and if the virtual origin is stored in an array descriptor, then the actual array need not be contiguous with its descriptor, and this is the usual case where the descriptor for the array parameters may be passed to subprograms and the actual array storage is stored elsewhere. In the same case, now we'll discuss about many more things, that is to discuss two and multi-dimensional array. So where we'll go ahead and detail, and that what we have to discuss, even though that has been asked of many times in the examination paper as well. So let's go ahead with the detail. That is two and multi-dimensional array. In this, a vector is a one-dimensional array where a matrix composed of the rows and the columns of the component is of two-dimensional array. A three-dimensional array is composed of planes of rows and columns. Similarly, the array of the number of the dimensions that may be constructed from the array of fewer dimensions, the storage representations, and assessing the formula for the vectors generalized rarely to the multi-dimensional array as well. The specification, and I'll discuss about the specification and syntax. In the case of the specification and syntax here, and a multidimensional array that differs from a vector in its attribute only in that subscript range for the dimension that is required, as in the Pascal declaration, where we can say that B of array which is 1, 10, minus 5, del 5 of real, and the selection of the components required that one subscript be given for each dimension. For example, that is BA2, 4. And we are now will discuss about the implementation as well. In the terms of implementation, a matrix is conveniently implemented by considering it as a vector of vectors, and that a three-dimensional array is a vector whose elements are vectors of vectors, and so on. And note that on that sub-vector that must have the same number of the elements of the same type. A two-dimensional array that can be viewed as matrix, and the matrix representation that may be a row measure or a column measure as well. In the terms of representations of the two-dimensional array, that to determine the number of the rows to skip over, that is your I minus L of B1, and that multiply with the length of the rows to get the location of the start of ith row, and then find the location of jth component in that row as for a vector. And thus if A is a matrix with m rows and n columns, and A is stored in the row major order, and the location of the element of I comma j is to be given as like in the form of alpha plus I minus LB1 multiply S, and then we have here else your, that is plus J minus LB2 multiply E. Where in the term of it, if I'm talking about that is your alpha has been denoting like a base address, and where the S is denoted as the length of the row, which is upper bound 1 minus lower bound B2, and plus 1 multiply A, that has been represented here as well. and that is your lower bound b1 and lower bound 1 and upper bound 1, that is representing the first subscript, and that is the lb2 and ub2, that is the lower bound and the upper bound on the second subscript has been represented here. Let's go ahead with a diagram that has been representing the descriptor, that is your dope vector, and other than that that has been representing the value of the m as well, and the storage representation of the component as well. So let's go ahead here. So with this we have here, and that is your here. The first we have is your VO, then LB1, which is equals to 1, then UB1, even though that is also equals to 3, then LB2, which is equals to -1, and that LB, after LB2 we have UB2, which is equals to 1, and then we have E, which is equals to 1, and then we have a shaded region here as well. This I will be representing you, and then we have here in the terms of it, if I'm talking about, this is your virtual origin. Then we have your, this is your lower bound, on subscript 1. Then we have upper bound on subscript 1. Then we have lower bound on subscript 2. Then we have upper bound on subscript 2. Then we have here is your, that is your size of component. In this from VO till E1, that is your comes under in it, and that is known as descriptor or a dope vector. And now with this we have here the another one, that is your I value of m, and from here till the last one, that is comes under known as storage representation for components, and this is your m 1 comma -1, this is m 1 comma 0, this is m 1 comma 1 from 1 comma -1, and this is your first row. Then we have m 2 comma -1, m 2 comma 0, m 2 comma 1. So this from here, this is your second row. Then we have m 3 comma -1, m 3 comma 0, and m 3 comma 1. This is your third row, and this is further exceeded. This is known as your the storage representation for the components as well. Let's go ahead in a detail the another one, that for collecting the constant term, this simplifies that s equals to upper bound on second subscript, that lower bound second subscript plus 1 multiply e, and that is vu equals to alpha minus lb1 multiply s minus lb2 multiply e, where the L value, which I had told you about it, and we had find it out as well, and that is of a I comma j equals to VO plus I multiply S plus J multiply E. So here that the subscripting the operation using an accessing formula is used to compute the affix that offset of a component from the base address of the array, and is similar to that of the vector as well. And similar to the vector case, E is the size of each component and S is the size of the row of a matrix, and this allows the VO to be easily computed as well. In the same case, while going ahead here as well, that you have to note that the VO, S and alpha and E are the fixed, and when the array is created and thus needed to be computed only once and stored, that the VOS in the vector case of the virtual origin, and the representation of the location for a 0 comma 0 if it would be existing in the array, the worst case computation necessary on each axis, then that becomes that lower value I comma j equals to VO plus I multiply S plus J multiply E. And then the higher dimensionally array, if I'm talking about that, the generalization of the formula to the higher dimensions is a straightforward, and that the following general algorithm that can be used to allocate the descriptor on the array creations and for accessing the array element as well. We assume that we have an array of AL1 and that U1 and then till ln and UN of a dimensions, where the L of I is the lower bound and U of I is the upper bound of and E is the size of the each array element, and the array will be stored beginning at address alpha as well. Where the first we have your computations of multipliers. Higher dimensionality array. The first we have is your computation of multipliers. In this, each multiplier, that is m of j, is computed as follows, and when we tend at mn equals to that is equals to e, and for each I equals to n minus 1, then down to 1 as well, we will compute it at in the same case we'll compute of m of I equals to upper bound I plus 1 minus lower bound I plus 1 plus 1 multiply m I plus 1. And for the next we have is your computation, and in the same case the computations of the virtual origin here. The computation of the virtual origin, if I'm talking about here, that where we'll say that VO equals to n I comma 1 L of I multiply m of I here. So this is the multiplier mi and the virtual origin that can be stored in the runtime descriptor for the array as well. The third we have here, that is your address of array. In the address of the array here, that is that array element here, that is the address of the element, where we can say that a si till as of n, and that is given by VO plus N I equals to 1 S of I multiply M of I. Now we'll go ahead to discuss about what do you mean by the record data structure, and we have to discuss about it, the record data structure with their definition, the specific, and you know, that is the syntax of them. So let's go ahead to discuss about it. So the first we have here is your, that is record data structure. In this record data structure, if I'm talking about, so here that the record that can be described as follows, like in the form of the definition, if I'm talking about, so the data structure that composed of a fixed number of component of different types is usually termed as a record. And specification and syntax, if I'm talking about, both the records and the vectors are the form of the fixed length linear data structure, but records differs in the two ways. The first way is that the components of the record that may be heterogeneous of mixed data types rather than homogeneous. The second is that the component of the record are named with a symbolic name, that is your identifiers, rather than indexed with a subscript, so that the C syntax for the record declaration, that is struct in C, is a fairly typical. So for that we'll go ahead here. With this case, that is your struct employ type, then int id, then int age, float, that is your salary, char, depth, that is your department, then employ. For that, the declaration that defines a record of a type employ, and the type consisting of the four components of the type as well. Whereas that the declaration defines the record of a type employ, type consisting of a core component of types, that is integer, integer real, character, with the components name id, that is your age, salary, department respectively. Employ is declared to be a variable of type employ type, and that is a subsequent declarations of the other variable of the type employ, that type do not need to give the record of the structure for the employ type. To select a component of the record, one writes in the C, that is your employ ID, employ salary, the storage representation that will be in the form of like this is your ID, then we have an age, then we have salary, and of course this is your department. So here in the same case, if I'm talking about here, that is your that ID, if I'm talking about, that is your 99312, and for the age, here we have age is your 27, and the salary is 290.10, and of course the department that we have is Z. So here in that the attribute of the record are seen in the prior declarations, and for that the number of the components. The second is that the data types of the each component, and the third we have here is your that the selector used to name each component here. And in the same case, if I'm talking about here, so that is your the component of a record that are often called fields, and the component name, then that the field's name, and that records are sometimes called structures as in C, and the component that selection in the basic operation on a record as in the selection employ salary. This operation corresponds to the subscripting the operations for the array, but with one crucial difference is that the subscript here is always a literal component, that is name, it is never computed or value here as well. In the same case, if I'm talking about moreover about this, then I will discuss about the information hiding as well. Somewhat related to this information hiding, I will just inform you about it, that the information hiding hides the detail of an object or a function. We will talk about the inheritance as well, that is the inheritance is the passing of information among a program component implicitly, and the tree structure that will done with it will do with that, and that is comes under the tree structures that can be used to evaluate the arithmetic expression. And after that we'll discuss about the control statement that like branching, looping, jumping, that are used to be alter the execution of the program as well. Let's go ahead with the detail, and that is comes under it, that they can ask you is what is information hiding, and that we'll discuss with their modules as well. Let's go ahead here. So here the first point we'll discuss about it, and that is your information hiding. In the case of the information hiding, that the information hiding is the process of hiding the detail of an object or a function as is shown by the heading as well, and that the hiding of these details that results in an abstraction, and which reduces the external complexity and makes the object or a function easier to use as well. In addition, the information hiding effectively decouples that the calling code and from the internal working of the object or a function that being called, which makes it possible to change the hidden portion without having to also change the calling code as well. The encapsulation is a common technique which programmers use to implement the information hiding. To understand the design of the language facilities for the programmer that define operations and the data type, it is important to understand the abstraction as well. On a large program or even one of the moderate size, when all its details are considered at once, then easily exceeds the intellectual grasp of a single person, that to construct a large program and a form of a divide that to conquer the strategy that must be used. And even though the program is divided into a set of components, often that called the modules as well, and each modules that performs a limited set of operations on the limited amount of the data as well, and this keeps intellectual control over the program that designed the process as well. So talking about the modules designed have generally followed the two approaches here. The first approaches here that we'll talk about, that were the modules and design. So in this module design has generally followed two approaches. The first approach is that the modules represent the functional decompositions of the program, and the second module is that the modules represent a data decomposition of the program as well. We are talking about in the detail here that the functional design that has been the method of the choice for many years, and however to see that what is wrong with the method, consider the section that data type and a section data type, and to compose that program into the functional unit, one programmer might be develop the registration function that would create a section and add students that to sections to assign the instructor to a section as well. And that for that another program that might perform class maintenance functions, such as your drop and add of the student from or to the section here, and entering the grades for each student, and sending home bills to pay for each such courses. And in each case that the programmer must know the detail of what both of the sections and the students are, and there is a little simplification in the terms of it if I'm talking about, and that is the simplification of the knowledge that required to build each component here. And in the same case that the however by creating that a model based on the data modelizations, however by creating a model based or the data modelizations that cause simple abstraction, most of the drawbacks are avoided as well. Building a section's abstractions and then using it in other modules are just such a simple abstraction, and that the specification of that data type is all that must be understood to make of it, and that the implementation detail are hidden and that can be ignored as well, and thus the programmer designing the overall strategy for assigning the students to the section in a programmer that can forget about exactly how sections are implemented and remember only that student that can be assigned to a section as well. The section have a structure and as well as the room numbers and so on as well. Let's go ahead to discuss about it, and that is, what do you mean by inheritance? So here, and what do you mean by inheritance here? That the mechanism that allows us to extend the definitions of a class without making any physical changes to an existing class in inheritance. And inheritance lets us create new classes from existing classes, and any new class that we create from an existing class is called a derived class, and that is existing class is called as well as the base class as well. So let's go ahead with a diagram here, that a flow diagram, we can say that in reference towards the inheritance here. So here in this, that is your base that comes under the derived 1, and that is your derived 2, and this is your derived 3. Okay, so in this same case, that the inheritance relationship that enables the derived class to an inheritance feature from its base class, and the furthermore that the derived class that can add a new feature of its own, and therefore that rather than to create a completely new class from scratch, we can take an advantages of inheritance, and even though we will reduce the software complexity. For example, in C++, we have 5 different types of inheritance. That is, namely, the first we have here is your single inheritance. In the single inheritance here, that it is an inheritance hierarchy wherein one derived class inheritance from the one base class. So that I will show you with the help of a diagram here, and that comes under in it, like this is A and there is one class, that is B. So here that it is the inheritance hierarchy wherein a one derived class inheritance only one base class here. The second we have here, the second one, that is comes under known as multiple inheritance. In multiple inheritance, that it is the inheritance hierarchy wherein one derived class inheritance from multiple base classes. Like if I'm talking about here with the help of a diagram, so you can go through with this, that this is A class, base class, that is your B, and that inheritance class C. Okay, this is a multiple inheritance here. The third one we have here is your, that is the another one is your hierarchical inheritance. In the hierarchical inheritance here, it is the inheritance hierarchy wherein the multiple subclasses inherited from one base class, and that is comes under in it, and we can say that with the help of a diagram here, it is the base class is A. So this is your A, this is B, this is C, this is D. This is a hierarchical inheritance. The next we have the fourth class, we have the fourth inheritance we have is your multi-level inheritance. In the multi-level inheritance here, it is the inheritance hierarchy wherein the subclass act as a base class for the other classes, and for the multi-level inheritance we'll go ahead with the diagram here, and that comes under in it as your in the following way, that is, this is a class A, then we have a class B, and then we have a class C as well. So this is multi-level inheritance. The fifth and the last inheritance we have is your hybrid inheritance. In hybrid inheritance, that the inheritance hierarchy that reflects any legal combinations of other four types of inheritance. So here that we have, then that is split it into two, and even though that has been coming towards one. So this is your A, B, C, and then of course D. This is your hybrid inheritance. Now we'll discuss about more in detail, that is, what do you mean by abstraction? In the term of abstraction, that has also been asked many times in your examination paper, and in the terms of it, that data abstraction refers to providing only essentials information to the outside world and hiding their background detail, that is to represent the needed information in program without presenting the detail. And the data abstraction is a programming and design technique that relies on the separations of interface and implementation. In terms of C++ programming, the C++ classes provides a great level of data abstraction, and they provide a sufficient public method to the outside world to play with the functionality of the object and to manipulate object data, that is the state, without actually knowing how class has been implemented internally. And there are the two broad types of abstraction. The first we have here in that same case is your functional in the reference towards it, that is your functional abstraction. The second we have data abstraction. In this functional abstraction and the data abstraction, here they are the two broad types of the abstractions here. The main difference between the functional abstractions and the data abstraction is that the functional abstractions refers to a function that can be used without taking into account how the function is implemented, and the data abstraction that refers to the data that can be used without taking into account how the data are stored. And there is also a difference in the way that the access takes place in the functional abstraction and the data abstraction as well. In a functional abstraction, access that to the functions provided through a specific interface defined to invoke the function, and in contrast, in the data abstraction, that access to the data is provided through a specific set of operation that is defined to examine, the manipulate, and that the data. And for instance, when a programmer is using the C++ standard data types, this means that the users are using the concepts of the data abstraction, and when using the data types, the users are not concerned with how the data is stored, but they are concerned with what operations are provided and what properties are supported. And with this, that the reason for the use of the abstractions is to be as follows. We'll discuss one by one. Reasons for use of abstraction. In this, the first reason we have a flexibility in approach. The second we have, going through with second, the first we have flexibility in approach. In this, by hiding the data or abstracting the detail that are not needed for presentation, the programmer achieves the greater flexibility in approach. The second we have is your enhanced security. In the enhanced security here, the abstraction gives the access to the data or the detail that are needed by the user and hide the implementation detail, giving enhanced security to the application as well. The third we have here is your easier replacement. In the easier replacement with the concept of abstractions in an object-oriented programming language, it is possible to replace the code without recompilation, and this makes the process easier and saves times for the users as well. The fourth we have is your modular approach. In the modular approach, in the object-oriented programming languages such as C++, the abstraction concept that helps the users to divide the project application into the modules and the test of each of them separately, then all the modules are integrated and ultimately tested together as well. Let's go ahead with the detail, and that what we have to discuss is what do you mean by the polymorphism. And what do you mean by polymorphism here, and that what we have to discuss in a detail as well. So in polymorphism, some of the things we have to know very well, and that is the polymorphism means that the ability of a single operator or a subprogram name to refer to any number of the number of functions that definitions depending on the data types of the argument and that results. For example, in an expression we'll talk about 1 plus 2 and 1.5 plus over 2.7. So two different plus operators are represented. So and that the integer operator, if I'm talking about the integer operator in the first and the real operator in the second. So the use of the generic and the adder allows to the limited overloading of function, and where the multiple instances of functions are compiled. So polymorphism is generally applied to a function where a type is one of the arguments, and that the identity function that can accept arguments of any type if we define ident as in the form of we'll go ahead, that is your fun ident x equals to x, and we get the response as well in the form of like fun ident x equals to x, and val ident equals to fin, that is your tends to x. So it signifies that the identifiers, that is a function that takes an argument of a type that a, and that is any type, and any returns an argument where that of type a, and that is the same type. And for type parameter a, that's passing integer strings and integer list argument to the ident are all valid here. For ident here, that I'll talk about like that is your ident 3 val it is equals to 3, and that is your int here. So in that same case, we'll talk about the polymorphism. Let's go ahead to discuss about the another question that has been asked of 10 marks, and that is what do you mean by a sequence control or a control structure? Explain. That has been asked of 10 marks, so you have to be very well prepared with this, and that is your sequence control and control structure. In the sequence control and a control structure, this as I told you about it, that has been asked of 10 marks, so you have to be very well prepared about it. And in this, the control structure is a programming languages provided the basic framework within which operation that and the data are combined into the programs in the sets of program, and the sequence control combines the data and operators that the operations and organize them into the complete executable program, and this involves the two aspects, that is the control of the order of execution of the operation, and both primitive and the user defined, and the control of the transmissions of the data among the subprogram of a program, and which we termed data control. That the sequence control is categorized into the two categories, and that may be implicit or explicit, and sequence control structures that may be conveniently categorized into the four groups. That the first we have the expressions form the basic building blocks of the statement, and that it expresses how data are manipulated and changed by the program. The properties such as the precedence, rules, and parentheses that determine how expressions becomes evaluated. The second is that the statements or the groups of the statements such as the conditional and the iteration statement that determine how control flow from one segment of the program to the another one, and that the declarative programming is an execution model that does not depend on the statement but nevertheless the cause execution to proceed the program, and that the logic programming model or a prologue is an example of this. And subprograms such as your subprogram calls and coroutines form a way of to transfer control from one segment to the program to another, and this comes under the sequence control and the control structures as well. Let's go ahead with the detail with another one, that is what do you mean by implicit sequence control. In the implicit sequence control, even though that has been asked for 10 marks as well. Implicit sequence control. In the term of implicit sequence control here, which has also been asked of 10 marks, and that what we have to be gone through with, and that implicit or a default sequence control structures are those defined by the languages to be in effect unless modified by the programmer through some explicit structure. For example, most languages define the physical sequence of the statement in a program as controlling the sequence in which the statements are executed unless modified and unless modified by an explicit sequence control statement. Within expression, there is also commonly a language that is defined hierarchy of an operation that controls the order of execution and operations in the expressions when parentheses are absent. In other words, in implicit program execution, the control passes to the statement one after another and until there is a conditional statement like if then else or loop like for a while etc. In a looping statement, that the control does not leave the block until the condition will be true or false, and most of the structured programming languages using the implicit sequence control mechanism. For example, consider the expression 5 plus 10 multiplied 2, so that in C, and that is since there is no parenthesis that tells which operation is performed first, but C language defines that abstract has precedence higher than plus operator, so it's solve first. The resultant will be your 25, because in the same case it will solve this abstract one, then after this the resultant will be the 25 here. And so the implicit sequence controls tells the sequence of the operators and that are defined by the programming languages as well. And the same case, since it is built in the programming languages, so it also called default sequence control. And if implicit sequence control is considered, then of course the programmers modify the implicit structures by some explicit structure as well. The programmers provide the parentheses within the expressions to change the order of execution of program operation in expression, that is your if I'm talking about the expression that is your 5 plus 10 abstract 2. In this we can first solve the addition plus operator and then multiplication operator, so that the resultant will be the 30 instead of 25. So the programmer that can change the implicit structure that define the programming languages and provide the explicit structure within operators, that the programmers provide go-to statement and that shifts control from the statement to the another statement. And for example, the statement 1 if I'm talking about, so with this we will be having a statement here, and that what we'll have to go through is, in that same case we have a statement here, that is if, that is your condition bracket statement 2 else go to 1, and then so this is in this statement, if condition false then control go to statement 1 here. Let's go ahead with the further one, and that what we have to discuss about what do you mean by the explicit sequence control, even though we had discussed about the implicit sequence control. So now we'll discuss about explicit sequence control. In the term of explicit sequence control structures are those that the programmers may optionally use to modify the implicit sequence of operation that defined by a language, and that the early programming languages were modeled after the underlying actual machines that would execute the program, because the machine consisted of the memory locations. An early language example like Fortran, Algol, and that is modeled these with simple data type directly translate into the machine object. Examples: C float and a Fortran real into the hardware floating point, and C int into the hardware integer as well. And with the simple statement consisting of the labels and the branches as well, the transfer of the control is most often indicated by the use of the goto statement to the explicit statement with the given label name as well. The two forms of the goto statement that are often present in many languages. The first we have here in that same case, that is your unconditional goto. So here we have unconditional goto. In the unconditional goto here, within a sequence of the statement, an unconditional goto such as like go to next, that transfers the control to the statement labeled next, and that the statement that following the goto is not executed as a part of the sequence here. The second we have your conditional goto. This is your unconditional, and that is your conditional, and that is your goto. In the conditional goto here, that within the sequence of the statement, a conditional goto such as like if a equals to if a equals to 0, then go to next. So in the same case, that transfers the control to the statement labeled next only if the specified condition holds. Use of the goto statement that leads to an unstructured design of a program. For example, much of the formal modeling leading to an axiomatic correctness mode of the program design that depends on the reasonable control structure for a program. In fact, the axiomatic model given in that section that does not easily permit the inclusion and that inclusion of the data that is the goto statement. More important, it has been shown that the goto statement is a superfluous and program that can just as easily be written without the gotos, and most students learn programming in the C or a Pascal without ever being taught that both language contain goto statement, and that the break statement also leads to an unstructured programming languages. Some languages such as C include a break statement as the form of the structured explicit control as well, and usually the break causes the control to move forward in the program to an explicit point at the end of the given control structure. Thus that break in C that causes the control to exit the immediately in closing while for or which switch statement as well. And C also includes a related continue statement. This causes the control to move forward to the end of the current loop body, and in the same reference towards it that in a while or for statements such thus a break will exit a loop, whereas the continue will iterate the loop again as well. In the same case, now we'll discuss about it, that is discuss the sequencing controlling for evaluating the expression. Sequencing controlling for evaluating the expression. In sequencing controlling for evaluating the expressions here in the terms of it, if I'm talking about, so here that to evaluate an arithmetic expression that generally we use in the form of the tree structure representation, and the structure of and that expression that may be represented by an expression tree. An expression tree is a recursive data structure which are defined as, the first we have your elementary tree. In the elementary tree, an elementary tree consists of a single node for an elementary operand, and the second we have is that is composite tree. In the composite tree, if I'm talking about, so that is that the root node top to the tree that represent an operator, and each operand is representing by a subtree. In a tree structure, the root represent the main operations. The node between the root and the leaves represent intermediate level operations, and leaves represent constant. And for consider the root of the quadratic equation, when you are gone through with the mathematics section, you have gone through with the formula plus minus under root b square minus 4ac and upon that is your 2a. Okay, this is a formula where in the higher level language such that Fortran, such as Fortran, that the equation represented in the form of which will be in the form of like x equals to minus b plus what and then b 2 minus 4 abstract a abstract c then by 2 abstract a. So this has been represented the formula only here in the form of the Fortran, and that the tree representation will be in the form of when we are going towards it, that is first to evaluate the expression that we must follow the precedence rules for the following operation, that is your prefix, infix and postfix. And for before that, if I'm talking about here, so that is comes under in a very tree structured manner, and that comes under in it like in the form of this is so after this then we have expressions as well. So this has been representing that formula only. So this is your divided sign, then plus, then of course the abstract here, and then of course we have here 2a, this is square, this is your minus, and that is your b as well, this is minus power abstract, then again we have an abstract, this is c, this is 4, this is a, this is b, and this is 2. So that has been represented here. Now we'll talk about the prefix evaluation. In the term of the prefix evaluation here, in a prefix evaluation, we can evaluate each expression in a single scan of expression, and that the expression that can be evaluated with the help of a stack. Let p in the given expression, then it is executed in the following manner, and in the next term in a p is an operator then put into the stack set of the argument that count to be the number of the operands needed by the operator. If the next item of the p is an operand, and then push onto the stack as well. If a top n entries in the stacks are operands that are needed for the top n array operator, we can apply to the top operator to these operands and replace the operator and an n operand by result as well. The second we have here is that is postfix evaluation. In the postfix that evaluations here, that the operators in postfix that notation that follows in an operates its operands as well. The postfix notation that uses the stack for the evaluation, and let p is a given expression, then it is executed in the following manner. And if if the next item of the p is an operand, then place it on the stack. And if the next item of the p is an array operator, then its n argument must to be the top n items on the stack, and then replace these n items by the result as well. The third, we have infix evaluation. In the terms of the infix evaluation, let p the given expression, then it is executed in the following manner. And infix notation is suitable for binary operations and a language that cannot use only infix notations. Therefore, we can use the mixture of infix with a prefix or a postfix. But to evaluate mixtures, it is very complex task, and when more than one infix operator appears in an expression, then parentheses are used at the right place as well. Let's go ahead with another one, and that what we have to discuss is what do you mean by the structured sequence control and iterative statement. Discuss the various flow control statement in a programming languages. Let's go ahead in a detail here. Structured sequence control and iterative statement. So it is the, or they can ask you discuss the various flow control statements in the programming languages. So with the same regard of it, if I'm talking about that, the flow control statement are used to alter the executions of a program, and if we don't alter the flow of the program, it will start execution from the main functions in the C languages, and that will continue up to the end of the program as well. And the three types of the flow control statement that are used in the C programming, and these were the along with the type of the statement that is used here. So these were the things that goes on very long way here, that what we have to discuss about it, and so that will extend the class more than 1 hour. So we'll continue with this class in the next coming classes. And first of all, with the regard of it, if I'm talking about, I will just tell you about the control statement, branching if statement, and the if else statement, that we'll discuss in the next coming class. So but for the branching, looping, and a jumping, that I will tell you about it, and that what we'll discuss in the next coming class. So for the structure sequence, as we had started, so I will just tell you in a short way. These are of three types. So here this is your control statement. That is your control statement, and this has been divided into three. That is your branching, and then you have looping, then you have jumping. In branching, what it comes under it, that is if, then if else, then if else if, and of course the switch. Then for looping here, that comes under in it, that is your while, do while, and of course for. For jumping, it comes under break, continue, and that go to. So that we'll discuss in a detail in the next coming class. And first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button, and please like, share, and subscribe to our channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In the same case, what we had cover up and what we have to cover up in the PPL, that is the principle of programming languages, that is unit 1. In this unit 1, what we had covered up, we had completed that unit 1. In the unit 1, we had completed the introduction part, and that is the role of the programming languages. Why study programming languages towards the higher level languages? Programming paradigm, programming environment, language description, syntactic structure, language translation issue, programming language syntax, stages in translation, formation, that formal translation model as well. In unit 2, that is a language properties unit. In the language properties, we have done about modeling languages properties, elementary data type, encapsulations, inheritance we had done, sequential control we had done, and subprogram control, that what we have to done in the next coming classes, and we'll complete with that as well. In unit 3, that is your programming paradigm. In the programming paradigm, we have to cover up the programming paradigm, that is imperative programming, statement types, procedure, activations as well. In the object oriented programming here, that what we have to cover up. In that same case, we have to cover up the grouping of the data and the operations, object oriented programming, and the functional programming. We have to cover up the elements programming in the type language programming with list as well. In unit 4, the other programming paradigm, that we have to cover up the other programming paradigm, logic programming, concurrent programming, network programming, language description, semantic method as well. In unit 5, we have to cover up the lambda calculus, that is a lambda calculus, introduction to the lambda calculus, simple type, subtyping, that what we have to cover up in the next coming class. So first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button, and please like, share and subscribe our channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Thank you, thanks for supporting us, thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on the comment box. Thank you.